because okay, so it was great hearing from you guys and the audience about being able to calculate the number of steps. It's something that I'm talking about the first day. I didn't know Fitbit would be here. So I flip it here, draw ball, and I give you a band. And the first question, how do these actually give you the readings? So anybody can make a guess what's inside the what's the sensor inside that gives the readings? Yeah.
3D accelerometer, and you've got the TI Bluetooth chip.
Correct.
And we have, what's the third chip? There's a third one.
Maybe a gyroscope?
Yeah, thank you.
Yeah.
Okay.
Okay.
No.
Along that line, correct? Along that line. And you guys were asking, how do we know whether the steps that are giving is accurate or not? So, just offhand, usually you don't see this, but these are all actually data gotten from the accelerometer data. Usually you do not see this. So, assuming that the data gets transmitted to you live, this is what you will see. It's all very noisy, and usually it's in 3 axes, X, Y, and Z. 3 axes, and you can't use this at all. So what is done is they go through we call it a low pass filter, but it's more like an averaging process. We try to average out, even out the values around here, and after evening out the values, you get a better curve, like the one in the middle. The next step you do is you go through we call it a derivative process to find out the local maximums. And you go, and all the zero crossings that you see over here are the local maximums. And what the software does is that they count the number of crossings over here, and that essentially gives you the number of steps that you take. And that is, on a nutshell, how such sensors they give you what the number of steps that you take every time you walk. So these are algorithms that are being used by such sensors, basically. Okay? And everybody okay? So, okay, ubiquitous nature of accelerometers, you see them all the time. So I believe you have something like this. You know that it goes through a landscape or portrait. Yeah. And how it does, again, the same thing, accelerometer. So we all know that you are standing on the ground right now. And if you take this to be the X, we know that the gravity is acting on me in this direction. And it's the same over here. Right now, the gravity is acting here on this direction. I turn it around, gravity now acts in this direction. And it's through this knowledge that the phone knows that, okay, I should switch the screen right now, because the sensor inside is telling me that gravity is acting on another direction. So that's basically it. And how it works is, that's how, and it is also used in so-called the airbags. So when you jam brake or when you hit something, essentially it detects a very strong acceleration, and that induces the airbag to pop up and to protect yourself. But how do they work? So this is a very simple example. So you have a spring. So this spring acts in one direction because of gravity. And over here we have one-directional accelerometer. You are standing to 3 dimensions. That will be here, X, Y, and Z. And depending on how you turn, it determines where your accelerometer is facing and essentially where your device is facing. And of course, if you want to embed it into a chip, you can't have balls hanging like that. So what they have is they embed this into a silicon. So this is an example of a silicon. This is the main body. These are all moving parts. So essentially your main body moves left or right, depending on the acceleration. And there are positive and negative charges attached to the green portions. Essentially when they move, they do contact. And it's through this contact that you know that, okay, this is now my acceleration force. And that's how essentially they work. So that is the brief introduction. Some of the reference points, Earth gravity is 1g. The speed bump is about 2g's. A space shuttle 10g, and this is a boxer's punch. Essentially, it's actually very big, 3g. It's actually very strong. So a very strong punch by a top-notch boxer would essentially send your head flying at the rate of 53 g. Yeah, you can see the expression. So yeah, essentially these are some of the reference points that we have. Yeah, and so for us, we are really a very small company. So about 2-3 of us. So we started off with very raw devices like this. We didn't even have wireless sensors, so it was done by a by a fixed wire to the laptop. And then we moved on to stuff from TI. This was the Arduino, then from TI. And we made our first few boards. These were our first few boards. And essentially, they weren't very small. They weren't very big as well. So the final board is this, 25 millimeters by 31 millimeters. I can show you a bit of a demo later. And this was the experiment that made us propel us to think that this is possible. So we had the accelerometer attached to the base of the tennis racket. We did a hit on the tennis racket. So we identified very, very different spots on the tennis racket. We have the sweet spot. You have the top, left, right, and everything else. We found this. You hit it on the sweet spot, it gives you a very, very nice curve. Very, very well damped. Very well damped. It book and you damp. You hit it on the dead spot, it gives you this. Very, very noisy. You get a very disturbing sensation. And essentially that is what causes your tennis elbow to happen. Because the energy is not being absorbed by the racket and is absorbed instead by your arm. If we just do a bit of processing, you can find that these peaks, they in fact refer to the number of the stroke that is being hit by the player. And these are just matrices that we have to determine whether are you hitting on the sweet spot or not. You notice this is at 40G and this is at 80G. There's a bit of difference in the scale. These are all sweet spot hits. These are all non-sweet spot hits. The interesting thing is this. The highest point of the sweet spot hits is in fact much, much lower than even the lowest point of the non-sweet spot hits. It enables you to very clearly identify whether it's a hit a sweet spot or not. So that's one very, very key thing that we found. We found that if you can do this, you can extend this concept to different sports, not only in tennis, but badminton, in golf, and any other thing. And that's how we came with this concept. We have one sensor for multiple sports. And for very, very small stuff, it actually makes a lot of sense. Because we don't have money and anything to come up with a lot of sensors, so we come up with just one. Which I can show you over here. That's one. The 25 by 31 millimeters one. We try to embed this into different so-called industrial designs, into different rackets or different attachments. And with just one industrial design, one integrated circuit design, we can sell this to different companies. They can do, we even pass them our PCBAs, and they do their own printing, do their own encapsulation, and they can do it for their own different sports. And that's how we've been trying to do it over the last few months. And over here you have the some casings that we tried to do. We're still doing it, but we find that to produce something like this, a plastic frame like this. Oh no. Anyway, don't feel sorry for me. I will save for dinner. Anyway, to produce a chip like something plastic like this, right, requires you to do molding. And each mold can easily cost up to 20-30K. So it doesn't make sense for a small company to have that kind of money to do this, because we really don't know the demand. So what we are doing right now is we are just selling the chips per se. We just sell, and we release our API as well, and if they want to, whatever they want to do with it, then we just try to increase our run rate in order to try to not die. Essentially not die, yeah. So just a bit of technical stuff. So we have the data coming in, and we create the model. So there are different verticals. So there's tennis, there's golf, there's fencing. We do the model creation. So for example, if a tennis player, a fencer does a certain stroke, we essentially collect that kind of data. We build a model of the data. And so every time another player does the same stroke, we'll compare that data with the model that was generated. And that will give them the reading. So that's about it. I will show a short demo of what. Actually, I was quite interested to know that you guys are very keen on the data. This is the kind of data that you are seeing. So probably it's very hard to make sense of it. But we do release such data to people. So what happens is that you on the sensor transmits data to your iPad. Maybe I should show you this first. So this is our application. So you can see there are different sports that are available. We show the first one, which is fencing. Does it work? Fine. Yeah, and it seems to be connected right now. So green means it's connected. Let's start about. Yeah. So for example, fencing will be doing something funny here, then he will boom, then another stroke comes out. It tells you the force of the stroke. So essentially, this force can be translated to a lot of things. For example, in boxing, you can find out what's the force that's being translated to. So I mean, the way it can be applied is a lot. Even for we have inquiries for soccer where they attach it to the feet of the person, and when the person kicks, they tell you what's the force that's being generated. Tells you for this particular application, it tells you the reaction time, which is the time from the start of the stroke to the end of the stroke, as well as the time between the lunges. So it sort of knows like what is the load that the person actually goes through. If we divide this time into so-called maybe about is 3 minutes, we divide it into maybe a few seconds, maybe 1 minute, 1 minute, 1 minute. You can roughly gauge what's the energy level of the fencer, whether is he able to sustain through the entire 3 minutes. So these are all matrices that are very, very important to either a sports person or to their coaches. Yeah, very interesting. Yeah. Yeah, of course.
It seems like your target audience is mainly for professional athletes and the coaches.
Actually,
so are you broadening up this wider range of consumers?
So the thing is that I have some channels at least to the people that are a bit more professional, and as well as to the manufacturers. A bit, not a bit. And they are the ones that are giving me such requests. So I service the requests because they will hopefully pay me one day. But so if consumers are saying that they want this, if I have the channels that Fitbit has, of course I'm going to be consumer, but I do not have them right now. I only have what I have. So that's why I'm doing a lot in such people. Again, what we are targeting is we have a platform, and we aim to be able to license the platform or even just to sell the hardware per se. So that is where money seems to be more readily available, rather than going into a consumer-based product and you need to spend a lot of money in marketing, you need to spend a lot of money in convincing people to buy a product, and that's something that I do not have. Yeah, but you can help me with it. Okay, any questions before I show you something else?
Taking your example of the kick in the football,
Yes.
should the sensor go in the ball or the foot?
Okay, that's an excellent thing. So the sensor will have to go into the foot. There are two models of doing it. The first thing, the sensor going to the foot will be very good if you are going to train the thing. You're using it for training. So you have balls that come to you and you just kick and you kick and you kick. You can know the strength that you have every time you kick. So that was something that we thought of for soccer. There was another company that said that they wanted something for hockey. So for that, the sensor has got to be in the ball because they want it to be a natural game, and they don't want it to be on the bat. So with that, what we thought of was, I will embed that into the ball. But what happens is that right now for this device, it doesn't have a so-called memory device. It doesn't have memory. So what will happen is I have to add in a memory chip inside this device so that they can store the data. And data is stored all the time when it flies up. When it comes back, then I will have to send it back. Yeah, so it's a different mode of operation. It's just a bit different, but it's okay. Anything else?
What is the, let's say it's coming from India, cricket is based in India. And I could very easily see how it could be very useful. The same problem as tennis level. If you middle the ball, then it should be a very different compared to not middling the ball. So, what things I could have to develop something like that for cricket?
I have to see what are the specs that are required. Yeah, so many of the specs, but what we target always is how can we use the same hardware to customize the data in order to fit it for cricket. So the good thing is that we also use the Bluetooth 4.0 stack, so it's low energy. And the iPhone, iPad devices, they are able to take in multiple Bluetooth 4.0 devices. So I can, in theory, I can attach 2 or 3 to your bags, and I can let the person do a swim. And in theory, I should be able to get, based on the location of the sensors, where exactly is the ball hitting it. Yeah, because of difference in the acceleration readings diameter. In theory, I should be able to do that. a very simple thing that we did. This it may look a bit daunting, but the reason it's daunting is because we are working with this for the sports council, so they want it to look a bit more professional or something. I don't know if this looks professional, but I don't know. Yeah. Anyway, yeah, you browse for the fancy data over here. You verify the data. Yeah, and then you analyze it. Then essentially the graphs come out. So you don't really need to go and view through your other graphs or anything, and then always put down the data. And this will give you one axis, and all the other components will be down here. So it makes it very easy for people to download the data, play around with it, and of course, what I showed you earlier, the different drill downs data. So this will be the actual data. This is the smooth out data. This is the derivative data. I included one more, which is the smooth out of the derivative data, because I realized that it actually doesn't work very well if I analyze it. So I carry another quite low pass filtering to make it a lot smoother, so that the readings that you get will be a lot more accurate. So that's a very small demo that I have. So are there any questions? Yeah.
That's awesome. I want to know, are you looking at biofeedback? I mean, how do you close the feedback loop? At the moment you have to download, or you're streaming the data to the iPad.
Yes.
But do you stream anything to the person using the racket or using the club?
Oh, so currently what happens is the data is streamed to the iPad, and at the same time it's being streamed to the server. So we have a server that's taking all the data. The interface for the web isn't done yet. So, and the interface to the web will let you connect to Facebook as well. So we're trying to complete the loop in that manner. Yeah. So that's how we try to do it. Yep.
How do you account for human variation, like in strength levels, for example?
Yeah. So we try, but it may not be the best. It may not be the best. Yeah. So we have like your age, your gender, your weight, especially your weight and your height.
Yeah.
The main thing is the length of your arm, and in a smaller way, the type of racket that you're using. Yeah. So these are the two things that are most crucial. Because we are using a few formulas, and those formulas they depend on like the weight that is being, the mass of the thing that is going to hit the projectile, and also the length of it. So these are the two things that will determine how accurate this is. However, I mean, to be very frank, all these are really more of an estimate. I still cannot get them to be like 100%. Yeah. So they are more of an estimate. These are formulas that are there, and I'm using it. But how accurate they are, to be very frank, I cannot give an exact answer as well. I'm sorry, you asked.
Yeah, what's the range like?
Yeah, this is a very good question. Because this is plus minus 16 G. So it can detect most things, but it cannot detect a boxer punch because it's too high. Surprisingly, it also cannot detect walking. So to detect walking, I need to reprogram this to make it plus minus 2G. So to explain a bit more, the chip inside, it allows you to go up to plus minus 16G. However, if I do it at plus minus 16G, I can get high impact sports, for example, tennis or what, I can detect them well. But for low impact sports like walking, I cannot detect them well because the resolution is too small. So I need to reprogram it to plus minus 2G in order to detect things like walking, because then the variation will be large enough I can see the graph. Yeah. But that's a very, very good question.
So for boxing,
not yet, because it's okay. For 70G, the price of the chip becomes very, very high. So plus minus 16 is still considered low G sensor. Once you go higher than that, it becomes a higher G sensor, and that goes into a bit of military grade, and that becomes a lot more pricey. I think so. That was my impression. Sorry.
and also this transmits to the iPad, right?
Yes.
So what is that?
Bluetooth. We are using Bluetooth. Actually, it's about 30 meters. Yeah, BLE.
I have
Yes.
in terms of training, how do you tailor to the types of training? And then at the end of the day, with all this data and whatnot, what would you utilize it? How do you keep it for a specific type of sports? And who do you work together with all of this presets for all trainings?
Correct. So currently we are working together with, as you said earlier, with some professionals. because they were saying that, okay, I need to use this for certain sports in a certain way. And in essence, we are tailoring the how we analyze the data to what their requirements are. And that is how we go on to different verticals. That's why you see in iPad we have verticals for fencing, we have verticals for golf. Because we have engaged professionals in those areas, and those are the so-called, we can get feedback from them. And we are, in a way, if the point finish, in a way we are using these data in order to sort of make sure our product works quite well. And then we are using them as our test data testers, and with that we can use those algorithms, and we can in a way tell other sports schools that we have this data, we have this way of analyzing, and it has been verified by certain parties already. And that's how we're doing.
All right.
Okay.
Thank you, Donny. That's
Thank you very
awesome.
much.